Today we're going to do an introduction to rotation. So we're going to start by comparing the difference between rotation and revolution. When we say the word rotation, what we're describing is an object moving around an internal axis. So for example, the Earth spinning on its axis would be an example of rotation. Revolution is when an object is moving around an external axis. So here we have the Earth orbiting the sun, and this would be an example of revolution. So the Earth is both rotating and revolving at the same time. Here we have a merry-go-round, and as you can see that these horses are moving in a circle, the platform is rotating, and one of the questions we can ask is, how do you measure the speed when something is rotating? So the first thing we can measure is the rotational or angular speed. And the symbol for this is the Greek letter omega. And this is the number of rotations per unit of time. So if you look at an individual horse, how long does it take for it to go all the way around? And it doesn't matter which horse you sit on. It could be close towards the center or closer towards the edge. It will take the same amount of time to make a complete circle. Now, the horses towards the outside is going to travel a bigger distance. The horses closer to the inside will travel a smaller distance, but the rotational speed, they will all have the same rotational speed because they will take the same amount of time to make one rotation all the way through. And so we can describe this motion using RPM, the revolutions per minute, because this horse is going all the way around. And so the revolutions per minute, or we can describe it as revolutions per second. Next, we can also measure what's called the linear or tangential speed. And the symbol for this is V. So I want to just take a moment and illustrate this. So here we have a circle, and let's say that this is going in this direction. So this is a top-down view of the merry-go-round. It's going in a clockwise direction, and it doesn't matter if you are sitting over here on this horse or on this horse. They will both have the same rotational speed. They will both make it all the way around in the same amount of time. However, they will have a different linear or tangential speed. The linear tangential speed is the distance traveled per unit of time. So if you remember earlier to what we talked about, what the definition of speed is just distance divided by time. And so since this one is a lot closer, it's going to go a shorter distance. It's going to have a smaller speed, while the one closer to the edge is going to have a faster speed. And the unit for the linear speed is meters per second or kilometers per hour. And it increases as you move away from the axis of rotation. So both horse A and horse B have the same rotational speed. However, they have a different linear speed because B is traveling a bigger distance, a bigger circle in the same amount of time. So B has a greater linear speed. So there is a relationship between linear speed and the angular speed or the rotational speed. So the linear speed is proportional to the rotational speed. So how fast it's rotating. So it's rotating real fast, you're going to have a greater linear speed. But also is affected by how far you are from the center of the circle, so the radius of the circle. So if you are closer to the edge of this merry-go-round, you're going to have a greater linear speed. If you're closer towards the center, you'll have a smaller linear speed. Now let's take a look at some examples of rotation problems. So question number 1, it says it takes a merry-go-round 8 seconds to spin once around. What is the rotational speed of the merry-go-round in revolutions per second and in revolutions per minute? So we're starting with 1 revolution in 8 seconds. And then we want to calculate the revolutions per second. So we just take 1 divided by 8, which is 0.125. revolutions per second. We can also write this as 0.125 RPS. Same thing. Okay, so now we want to calculate it in revolutions per minute. So I'm going to start with 0.125 revolutions per second. And then we're going to do a little dimensional analysis. So I know that 1 minute is equal to 60 seconds. I'm going to put the seconds on the top because the seconds will cancel out, which leaves me with 0.125 times 60, which we get 7.5 RPM, revolutions per minute. And I'm going to go ahead and box these two answers. All right, question number 2. A propeller spins at 850 RPMs. What is the rotational speed in revolutions per second? And how long does it take the propeller to go around once? All right, so we're going to start with what we're given, 850 revolutions per minute. And we want to calculate revolutions per second. Once again, I know that 1 minute is equal to 60 seconds. I'm putting minutes on the top because this way it'll cancel out. I get revolutions per second. So 850 divided by 60, I get 14.2 revolutions per second. And now I'm going to calculate how long does it take the propeller to go around once. So 1 revolution, so going around once would be 1 revolution, times, and I know that it takes 1 minute, that in 1 minute it goes 850 revolutions. So 1 divided by 850, and by the way, the revolutions cancel out here. So 1 divided by 850 is 0.0012 minutes. And then if I wanted to calculate it in seconds, I could take 1 revolution times 1 second over 14.2 revolutions, which is what I got from the first part of this question. And I'm putting revolutions on the bottom once again because they cancels out. And if I take 1 divided by 14.2, I get 0.070 seconds. All right, question number 3. When a Ferris wheel spins at 2 RPM, a rider on the outside of the edge moves at 6 meters per second. How fast will the rider be moving if the rotational speed of the Ferris wheel increases to 4 revolutions per minute? So here we can use proportional reason to answer this question. We know that the linear speed is proportional to the rotational speed times the radius or the distance that the rider is to the axis of rotation. And so since the rotational speed has doubled, this has doubled, and since they're proportional, however factor it changes on the right-hand side, the left-hand side will change by the same factor, which is also going to be doubled. And since originally it was moving at 6 meters per second, the answer is going to be 12 meters per second because that is double the speed, the linear speed it was previously. Now I am making the assumption that we are traveling on the same location, this Ferris wheel, that the R is staying constant. So that is going to be important. We are making that assumption. You can tell in the picture, all these rides are at the same distance from the center of the Ferris wheel. Question number 4. If the rider is 8 meters from the Ferris wheel's axis of rotation, what is the tangential speed of a bolt that is only 1 meter from the axis of rotation? So once again, we can use proportional reasoning. We know that linear speed is proportional to the rotational speed times the radius. And since this has the same rotational speed, but the radius has changed. I went from 8 to 1, so now it's 1/8 of what it was before. So now it's 1/8 of what it was before. So since they're directly proportional, whatever factor you change on the right-hand side has to change the same amount on the left-hand side. So this will also change by 1/8. 1/8. Okay, so if originally it had a speed of 12 meters per second, then we'll take 12 divided by 8, and we get 1.5 meters per second. So this bolt is going to be going much slower, or yes, much slower, because it's closer to the axis of rotation. All right, question 5 has multiple parts to it. A bicycle's wheels spin at 240 RPM as it travels down the street at 7.5 meters per second. How long does it take for the wheel to spin around once? All right, so we know that one revolution, we're looking for the time for one revolution. We can multiply 1 minute on the top, and on the bottom 240 revolution, and I have that information from this part of the question. And if I take 1 divided by 240, by the way, the revolutions cancel out, we get 0.0042 minutes. So this is how long it takes for the wheel to spin around once. And part B, the bicycle goes down a hill. At the bottom of the hill, the wheels are spinning at 320 RPMs. How fast is the bicycle moving now? So in this question, we can use proportional reasoning. We know that the linear speed is proportional to the rotational speed times r. And since the rotational speed has increased by 4/3. Okay, so if you take 320 divided by 240, we get 4/3. So this has changed by 4/3, which means that the linear speed will also change by a factor of 4/3. So what was the original speed? 7.5 meters per second times 4/3, and we get 10 meters per second. All right, part C. The bicycle starts up the next hill. The rotational speed of the pedals is 48 RPM. The pedal gear is 0.1 meter in radius. How long does it take the chain ring, the pedal gear, to spin around once? So we're going to start with 1 revolution because we're looking for the time for it to go around 1 revolution. And we know the RPM. 48, we're going to put 48 revolutions on the bottom because I want to cancel out the revolution, and I have 1 minute on the top. And then the revolutions cancel out, which gives me 1 divided by 48, which is 0.021 minutes.